Modify it. Okay, I'm going to modify this. I'm going to say sample mean of this. And based on previous pizza studies, a standard deviation of that. Okay, that right there, because it came based on previous pizza studies, that's telling you it's a sigma. Okay, let's do it. Let's do a Z. I'm going to make it a Z. I'm going to make it a Z test. I just made it into a Z by doing that. Okay, let's write out these things, shall we? All right, mu x bar. Is it a sigma or is it an S? We just decided that it was not, this was not from the sample, it was from previous studies. So that's not this. It's telling you it's this. Okay, and then you've got your N is 36. Okay, so the sample mean, 28.5, population mean, 30. This one is looking at what? Are they looking at less than 30? So that's giving you a clue as to what you're going to write for part A, your hypotheses. What's your hypotheses? This one always goes here. So the alternate is the less than. Okay. There will be no need to double on this one. Isn't that exciting? No need to double. Okay, so we've done part A. Now let's do part B. Let's draw the curve, and then we're going to do a Z test, which is fun. That's going to remind us of what we did on the other pages. Okay, let's do it. So we draw our thing. 30's in the middle. 28.5. Well, that's the messiest 28.5 I've ever seen. 28.5. Okay, now, since you're using Z, you can go back to your old method of using the real mean and real mean numbers, as long as you make sure down here that you're going to have the standard error in here. You're going to have not the 3.5, but the 3.5 corrected for that size of 36. Square root of 36, sorry, but so that comes out to be 0.58333. So you can use your strategies from before. However, you still do need to find that Z statistic. And if you want to use a Z statistic, you can use it. Okay, so like if you want to use your Z numbers with the 0 and 1, you can, just as long as you've do it in Z world. Okay, so X bar minus the mean over, see, there's that number that I just figured out that number because like makes it a little easier. 28.5 minus 30 over 0.58333. I got negative 2.5714. So I finished part B. If this was your test, I finished that. Now part C, which excitingly, to find the probability that a Z goes below a negative 2.5714, you can put it in as, you can either use normal CDF. If you want to use the Z numbers, use them. Negative 10, comma, negative 2.5714, comma, 0, comma, 1. Notice that that's because Z. If you're in Z world, you need to use Z's mean and standard deviation. If you were using regular world, that's normal. They're both normal CDF. Both of these commands will give the exact same thing. Because the thing is, in normal CDF, you can specify a mean and a standard deviation. So that's why in normal CDF, I could have used the original numbers because I could have put in, I don't know, some like really low number, 28.5, comma, mean, comma, this thing, the standard error. These two, they're going to give exactly the same result. Oh, the TCDF? It's the same idea. It's finding the area on the curve, but the problem with the TCDF is that the curve changes for the size of the sample, whereas this one it changes for the mean and the standard deviation. So that's why in the TCDF you have to use the standardized score and then specify your degrees of freedom. And on this one you could use the standardized score with the standardized mean and standard deviation, or you could use the original scores with the original mean and standard error, and you would be able to get the same answer. If you plug these both in, you'll see they come out exactly the same. Label which one? 0. Oh, 0 is the mean. So like it goes like this. Here, I'll write it down. Normal, CDF, it goes left, right, mean, standard deviation, and like this might be over root n. If you have central limit theorem happening, then your standard deviation. See, if you had a size of 1, then over root of 1 would not have changed it. So like, but central limit theorem would change it to whatever the standard error is. So it goes left, right, mean, standard deviation. But on a TCDF, it goes left, right, degrees of freedom. And that's why you have to use the standardized scores, because the T curve is standardized and then being adjusted for the sample size. On this one, it's the normal curve is the normal curve. It's the same everywhere. It's 68, 95, 99.7, every single normal curve. But how did it get stretched for sample size and mean? I got an area of 0.0506. 0.00506. What do you think? Do you think you're going to reject or fail to reject? Reject. Thank you. You're going to reject. You have significant evidence to reject the null hypothesis, and delivery times are less than 30 minutes. You have the evidence that the times are less than 30 minutes, okay? Oh, yeah, this one works. Both of these get you the exact same answer. Which one? The first one, well, it's in the standardized world is why. But it does fit nicely with the TCDF. Hey, thanks. Does fit nicely with the TCDF. So like that, it means that you have evidence that the statement was false. You have evidence that the original statement of being equal to 30 is false, and that you have evidence that this is the truth, that the mean is less than 30. Okay, so like you have evidence that the alternative is true. And if you don't reject it, then you do not have evidence that the alternative is true. Okay. Okay. See ya. Okay. Oh my goodness. Okay, since the p-value of 0.00506 is less than alpha equal 0.05, we reject the null hypothesis, and there is significant evidence that the got to look at the claim up here, and we have to word it in terms of the alternate hypothesis that the mean delivery time is less than 30 minutes. And that's a wrap.